Good morning, everyone. Welcome back to our webinar series. Thank you for joining us. This morning, we are going to be hearing from Matt Cody first and then Lindsay Patterson, both of SLR Consulting, on investigating PFAS in Western Canada. Their presentation's about 40 minutes, and then after that, I will field questions to them from you. So I'm going to turn it over to Matt right now.
Great, thanks, Joe. So a big thank you to the Environmental Services Association of Alberta for the opportunity to deliver this webinar on per and polyfluorinated alkyl substances, or PFAS. Joe suggested that this seminar provide a general overview of PFAS, and so that's just what this presentation will be. Today,
Matt, I think we might be having a problem with your mic, your audio.
Lindsay Patterson and I will be.
I think we're still up. Matt, we're having problems with your audio. Matt or Lindsay, can you guys check your mics, please?
Yeah, my mic is, I think, fine. I mean, it has my audio right now.
Yeah, I can hear you. Matt, no one can hear you.
Oh, it's probably the island. He's on Vancouver Island.
Okay,
Something
everyone.
happened in the Salish Sea somewhere along there.
Oh, yeah, the Vancouver Island just slipped into the ocean. No,
Yeah.
just stand by. We'll see if we can get Matt working. Can you call him, Lindsay? Oh, wait.
Joe, can you just switch the video to your screen? To your slide?
Yeah. Yeah.
Hello.
Hello, are you back? Sorry, everyone is still waiting for Matt.
Well, I'll give Matt another minute. Oh, there you go, Matt.
No.
No. Okay, well, Joe, maybe I'll just get my slide deck up on my end and carry through if my sound's okay.
Okay.
Just
tell me when you're ready.
Yep.
I'll switch it to you.
Hello. Test.
Barely working.
Do you think you have audio, Matt?
No.
No. Okay. Well, I guess we'll just go from Matt. I'll just do my best with your portion of the presentation. All right, Joe, go ahead. Can you see my screen? Okay. Show
I have a black screen.
There we go.
There we go.
All right.
Sorry, everyone. We're back online now. Let's try this again.
Great. Joe, how's my audio? Hello?
Sorry, it's perfect. Thanks.
Okay, great. Okay, good. Just needed that validation. Okay, so today was going to be Matt, Cody, and I, but I think Matt's having some technical difficulties with the audio over in Vancouver Island. So basically, we're going to be broadly covering PFAS as it relates to the environmental industry in Western Canada. On the following slides and for the next 40 minutes or so, we're going to be touching on general PFAS chemistry, sources, special considerations for field programs, regulation at federal and provincial levels, remediation, and risk assessment. Hold on, it's not scrolling ahead here. There we go. PFAS are a synthetic group of chemicals that have been used in the manufacturing of a wide variety of consumer and industrial products, such as cosmetics, ski waxes, and all manner of water, stain, and oil repellency products applied to fabrics, carpet, paper, and other materials. Due to their common use in everyday products, almost everyone is exposed to low levels of PFAS, although in some cases, like the one described in this 2012 research paper from the University of Alberta, it's not always low levels. Residents in one particular Edmonton area home were found to have blood concentrations of one PFAS up to 200 times higher than the rest of the Canadian population. Based on the similarity of PFAS in the blood to that of chemicals used in carpet treatment applications, the researchers believe that the family's exposure was the result of multiple applications of carpet treatment products in their home over a 16-year period between the early 1990s and the mid-2000s. In addition to their presence in industrial and consumer products, PFAS have also been used in specialized applications, such as in fume suppressants for the metal plating industry, and as components of firefighting foams used to fight flammable liquid or Class B fires. It's probably the latter use in firefighting foams that is the most well known in the environmental industry today. The term PFAS encompasses both per and polyfluoroalkyl substances, a family of thousands of chemicals. The most recent estimate from the United States Environmental Protection Agency is that up to 4,700 individual PFAS chemicals may have been or may currently be on the global market. The perfluoroalkyl substances are those chemicals that are comprised of a carbon chain where the carbons are completely surrounded by fluorine atoms or are fully fluorinated, represented by the green circles on these molecular representations, which have been simplified for presentation purposes. Polyfluoroalkyl substances refer to those chemicals where the carbon chain is only partially fluorinated, so only a portion of the molecule is green or fully fluorinated. In the lower chemical, the blue circles represent carbon atoms that have hydrogen atoms attached instead of fluorine. The substances can have any one of a number of functional groups at its end, like carboxylic acids or sulfonates, represented by the red circle. It's this unique structure, a hydrophilic functional group or head combined with the hydrophobic tail, that gives these chemicals their unique properties. We tend to distinguish PFAS and name them based on the length of the carbon chain in the compound. Short chain PFAS have fewer than about 6 green parts, and long chain PFAS have more than that. The main point to remember about the structure is that the green or the fully fluorinated portion of the chemical is extremely persistent in the environment, regardless of carbon chain length, due to the strength of these carbon-fluorine bonds. And, since I've been working in my home office, my daughter very astutely pointed out that this PFAS resembles the very hungry caterpillar.
Lindsay, can I interrupt? I think I might have some audio.
Oh, great. Okay. Go ahead, Matt.
Yeah, excellent. Sorry to interrupt, and great job on my last joke there. As we were talking about PFAS, we should probably introduce what are known as the PFAS precursors. As Lindsay said previously, the term PFAS comprised a family of thousands of individual chemicals. Some PFAS are known knowns, things like PFOA and PFOS, substances for which there have been a tremendous amount of attention in the media, and there's a decent amount of research regarding their behavior in the environment. The PFAS precursors are known unknowns. They are larger polyfluoroalkyl chemicals that have the potential to break down in the environment into dead-end perfluoroalkyl substances, which do not degrade any further under ambient environmental conditions. This is a highly simplified representation of a precursor. The fluorinated portion of the chemical, the green part, which is the green part, as a precursor degrades as a result of environmental processes, the yellow, blue, and purple parts are expected to break off, but the green part will remain over time. Research suggests that a wide range of precursors can be present in PFAS source zones, depending on the formulation and the source product. But currently, with standard analytical methods, we're not able to quantify these precursors. Lindsay will touch on some advances in the laboratory evaluation of precursors in a later slide. This next slide here is just a quick summary of the information presented on the previous slides to help us understand how different types of PFAS and the nomenclature kind of relates to one another. In Canada, it's the perfluoroalkyl acids that are the focus of most regulatory efforts. The acids can be further subdivided based on the functional group associated with the chemical, whether it's a carboxylic acid or a sulfonic acid. We've provided a few examples here of some of the most common perfluoroalkyl sulfonates, so at the bottom left of the chart, and some carboxylic acids at the bottom right of the chart, so perfluorooctanoic acid, hexanoic acid, and pentanoic acid, as well as a commonly encountered polyfluoroalkyl substance, so 6,2-fluorotelmer sulfonate at the top right there. So under the Canadian Environmental Protection Act and its regulations, the manufacture, use, sale, and importation of some specific PFAS, as well as the products containing these compounds, is restricted in Canada. Internationally, 2 perfluoroalkyl acids are listed as persistent organic pollutants under the Stockholm Convention, with a third under review for inclusion. Why have there been these national and international efforts? It's because these chemicals are environmentally persistent, can accumulate in humans and wildlife. There are known health effects to humans and ecological receptors, and they have the potential for long-range transport. Hence, there is a need to reduce the potential for these chemicals to enter the environment. So now we'll kind of go into some of the sources. In Canada, we don't really have the same legacy of PFAS manufacturing as they do down in the United States in places like Minnesota, West Virginia, and North Carolina. Rather up here, it's the historical storage, handling, and the use of fluorine-containing firefighting foams that is probably the best known in the environmental industry as a source of PFAS to the environment. These foams have been used in training exercises as well as in emergency response activities, such as crashes and fuel spills. And where foams are not contained and recovered, the PFAS can then be released into the environment and infiltrate soils and run off into adjacent drainages and whatnot. Class B foams may also be released into the environment where firefighting equipment is tested, cleaned, and maintained, and where these foams are stored. Within the environmental industry, airports and military bases have been the main focus of PFAS investigations. In 2018, researchers at the Environmental Services Group of the Royal Military College published an article attempting to estimate the number of Canadian airports potentially contaminated with PFAS from the use of Class B firefighting foams. Based on their analysis, approximately 175 airports in Western Canada, so that's BC, Alberta, Saskatchewan, and Manitoba, were considered to be likely or potentially contaminated with PFAS. For illustration purposes only, and to help understand mass loading in comparison to other PFAS point sources covered in subsequent slides, it's estimated that if these sites conducted regular training of 2 to 3 firefighters annually, then this could potentially translate into the release of around 10 kilograms of PFAS per year at individual sites. So to put that number in context, the Health Canada Drinking Water Guideline for PFOS is 0.6 micrograms per liter. And if you were to try to achieve that concentration, you need to dissolve that 10 kilograms of PFOS in 17 billion liters of water, or about 6,500 Olympic-sized swimming pools. So that 10 kilograms does indeed represent a large load to the environment. Because foams have also been used to prevent the ignition of bulk flammable liquids during fires and spills, they are also likely to have been deployed at non-airport sites, such as large petroleum hydrocarbon storage and handling facilities. This is an old blueprint from one large petroleum storage facility that has had firefighting infrastructure in place. Again, for illustration purposes only and to help understand PFAS mass loading, we've put together an estimate of PFAS release per emergency response event based on some highly generalized assumptions. In this case, assuming that emergency responders would use a tank of 800 liters of foam to extinguish a flammable liquid fire. In a very large-scale event, it would be expected that many thousands of liters of foam could be deployed, which would result in a much higher mass than the 8 kilograms we've estimated here. We do want to emphasize these mass loading numbers provided here and on subsequent slides are quick back-of-the-envelope estimates that we put together, but they do seem consistent with importation statistics recorded by Environment Canada over a 4-year period in the late 1990s. Environment Canada data suggests that 14,000 kilograms of PFAS and PFAS precursors were imported to Canada over this time for use specifically in firefighting foams. Assuming on average those materials were ending up at 300 to 400 individual airports, military bases, larger petroleum handling facilities, and municipalities across Canada, this would translate to about 10 kilograms per year per location. It's important to appreciate that the composition of PFAS in the different Class B foams will have changed over time. So the PFAS that may have been present in the foams in the 1980s are not necessarily the same PFAS that we found in firefighting foams today. In Canada, firefighting foam with PFOA or PFOA and PFOS at specific levels are exempted from the federal prohibition of certain toxic substances regulation. However, the Government of Canada has recently signaled that the current exemptions will be removed from the regulations due to the discontinued use of PFOS in firefighting foams and the availability of the alternative products. In particular, manufacturers of present-day Class B foams have transitioned away from the use of PFOS and PFOA to products containing PFAS comprised of 6 or fewer carbons, fluorinated carbons, or C6 chemicals. So finally, some researchers have suggested that PFAS composition of firefighting foams sold in Canada are different in composition to the foams used in other jurisdictions like the United States with their military specification foams. Another point is that not all firefighting chemicals are sources of PFAS. These chemicals are associated with flammable liquid or Class B fires. Class A fire extinguishing materials are not expected to be a source of PFAS. The surfactant properties required to fight a Class A fire, such as the forest fire in the bottom left of the screen here, are completely different from the surfactant properties needed to fight a Class B fire, a flammable liquid fire, so the bottom right. With Class A fires, you want penetration of the combustible material, whereas with a Class B fire, you are looking for the foam to create a thin film over the flammable liquid, thereby isolating the liquid from oxygen. Finally, I'll put a plug in for my upcoming presentation on the management of PFAS firefighting foams that I will be delivering as part of the virtual EnviroTech conference occurring in June. This presentation will provide a more comprehensive discussion of PFAS and foams, and I promise you there'll be no technical glitches with that one. So some other sources, continuing on, although Class B foams are kind of the best known sources of PFAS in Canada and within the environmental industry today, they're not the biggest potential source of PFAS to the Canadian environment. In the same Environment Canada survey I mentioned on the previous slide, it was reported that approximately 600,000 kilograms of PFAS were imported to Canada between 1997 and 2000. Of this volume, the vast majority was used for water, oil, stain repellency purposes, with approximately 50% identified for use on fabrics, 15% for use on carpets, so similar to the Edmonton-based family that was exposed to carpet treatment products, and 20% for use on packaging. That's over 125,000 kilograms per year for these individual industries combined. And that doesn't include the mass associated with the importation of finished products with water, oil, stain repellency materials that have already been applied. The PFAS associated with fabrics, carpets, and packaging are expected to eventually make their way into the Canadian landfills and wastewater treatment plants and lagoons, and from wastewater treatment plants to areas where biosolids have been applied. Biodegradation processes in wastewater treatment plants are not effective at reducing PFAS concentrations. PFAS present in treated papers and in food serviceware also make their way into paper sludges and into compost where the green waste recycling programs exist. Some studies have looked at PFAS concentrations in Canadian landfill leachates, including landfills located here in Western Canada. This table here summarizes PFAS concentrations in landfill leachate at an undisclosed landfill that was compiled by Belinda Lee at UBC as part of her master's thesis, which is a publicly available document. The maximum concentrations here are high, and the mean concentrations of several PFAS are also elevated. This leads findings were also consistent with the 2012 leachate study completed by researchers at UBC, STS Axis, and the Department of Fisheries and Oceans. Of the Canadian landfills and PFAS studied by these researchers, the 4 predominant PFAS encountered in the leachate were PFHXA, PFPEA, PFOA, and PFOS. A review of global landfill leachate data completed by Hannah Hamid, Loretta Lee, and John Grace at UBC reported similar findings of the predominance of short-chain perfluoroalkyl acids in the leachate. That review also reported the mass loading of PFAS and leachate in one Western Canadian landfill was about 8 to 25 kilograms per year. So in many locations in Canada, landfill leachate gets directed into wastewater treatment plants. Researchers investigating PFAS concentrations at a Canadian wastewater treatment plant reported that PFOA was their most frequently detected PFAS, followed by PFOS and PFHXA. Median concentrations in wastewater effluent were relatively low compared to concentrations observed at other PFAS point sources. However, the researchers did report elevated concentrations in samples from some treatment plants, notably a maximum final effluent PFOS concentration of 1.3 micrograms per liter, or about 250 times higher than median levels. The study also estimated a median mass loading of PFAS at wastewater treatment plants of around 2 kilograms per year. Saskatchewan's Water Security Agency is currently undertaking a study in the province to evaluate PFAS concentrations in raw and treated wastewater. Reportedly, PFOA has been primarily detected, followed by PFOS. Finally, it's important to understand that PFAS precursors, which are present in wastewater influent, may be transformed into dead-end PFAS, which then don't degrade any further. Researchers have found that concentrations of dead-end PFAS are frequently higher in the effluent than the influent, particularly where the treatment includes an aerobic biological component, which may be enhanced depending on operating temperature and hydraulic retention times. It's for this reason that the presence of precursors in the influent, which will then undergo transformation, the reason for this is the presence of precursors in the influent, which then undergo transformation during wastewater treatment. PFAS also make their way into biosolids generated from wastewater treatment. The BC government reports an annual biosolid production rate of about 40,000 dry tons in the province, and Alberta's production is expected to be similar or higher based on the size of the municipalities there. Saskatchewan and Manitoba would be expected to have somewhat lower rates based on their population differences. In BC and Alberta, a significant portion of the biosolids are applied to agricultural lands as a beneficial reuse of the materials. And this approach has been endorsed by the Canadian Council of Ministers of the Environment. Researchers looked at PFAS concentrations in Canadian biosolids generated by different treatment plants. The median levels of one PFAS, so PFOS, was 13 nanograms per gram, which is similar in concentration to those observed by Environment Canada researchers in biosolid studies generated by one wastewater treatment plant in BC serving a small city. Interestingly, the 2014 biosolid study reported a maximum PFOS concentration from one treatment plant that was about 500 times higher than the median, which highlights the potential for PFAS originating from sources other than consumer products. In terms of mass loading, biosolids generated by wastewater treatment plants are expected to present a smaller source than liquid effluent. Finally, this slide presents the results of a joint study between Purdue University and the Zero Waste Group out of Washington. What they found is that the compost that included compostable waste food serviceware had higher PFAS concentrations of short-chain perfluoroalkyl acids and PFOA than compost generated solely from yard waste, so about 10 to 50 times higher. It is anticipated that PFAS are originating from the products that provide water and oil repellency to food serviceware, like clamshell containers and paper plates that often gets diverted into the food waste composting stream. Some researchers have suggested that PFAS concentrations in food packaging may be up to about 1% per fiber dry weight. In some Western Canadian municipalities, used paper plates and fast food bags are considered acceptable for inclusion in the green waste stream that gets composted. In Metro Vancouver, residents are encouraged to test their paper food packaging with the grease test to determine if it's safe for inclusion. If the grease doesn't go through the packaging, then it's not considered acceptable. So, and if you're still confused by this Metro Vancouver guidance, it's similar to the grease test used by Homer Simpson to ensure his diet contained maximum fat content in the window to weight gain episode of The Simpsons. In this image, Homer has rubbed his fish fillet against the wall, verifying its fat content by making the wall transparent. So it's just like that. It would be interesting to evaluate if a qualitative test completed by residents in Metro Vancouver is successful at reducing PFAS concentrations in composted food waste. In Denmark, they have set thresholds for total fluorine in food packaging, and in Washington State, they have legislated the ban of PFAS in food packaging. Using the Purdue study concentrations and doing some quick math, and assuming that the larger municipalities compost approximately 25,000 tons of food waste annually, this would translate to about 1 kilogram per year of PFAS. Other well-known sources, specialized applications of PFAS include their use as fume suppressants in the metal plating industry, particularly the chrome plating industry, where they have been used for health and safety purposes to help minimize worker exposure to hexavalent chromium vapors. This data from groundwater collected at one chrome plating facility here in BC. Even though the product was added to a plating bath in the interior of the facility, it clearly managed to migrate to exterior groundwater, resulting in some pretty elevated concentrations. Doing some back of the envelope math for illustration purposes based on typical reported usage of fume suppressant products at chrome plating facilities and PFAS content, it is estimated that fume suppressant use translates to between 0.5 and 5 kilograms of PFAS per year at such sites. Again, I'll emphasize that these were some quick calculations, but the math does appear to be consistent with Health Canada information that reported at least 3,000 kilograms of PFAS have been imported to Canada on an annual basis historically. Finally, it's important to realize that the individual PFAS associated with the different sources discussed on the previous slides will have changed over time. The Interstate Technology and Regulatory Council, or ITRC, in the United States has developed a nice fact sheet on the historical timelines and primary uses of different PFAS. Although the North American production of long-chain PFAS decreased over the past 10 to 15 years, the production of short-chain PFAS and substances known as fluorotelemers saw an increase as manufacturers simply replace one PFAS with another. And this is going to affect what we see in terms of background levels of PFAS in the environment. Global monitoring of PFOS in particular has generally observed a decrease in the levels of this chemical in the environment, in environmental matrices, including human blood. That is everywhere except in China, whereas China ramped up production of PFOS when North America phased it out. Unfortunately, we don't have a lot of historical monitoring data for the short-chain PFAS in order to evaluate temporal trends globally. But the general consensus is that we expect to see an increase in the levels of these chemicals in the years ahead. So it's at this point that I'd like to hand the presentation back to Lindsay to cover some of the environmental management considerations for PFAS impacted sites. Thank you.
Great, thank you, Matt. So knowing that there are likely numerous sources and mechanisms by which PFAS can be transported to different receptors, then the next question is, how do you look for them? In BC, the Society of Contaminated Sites Approved Professionals, or CSAP, commissioned a guidance document to assist environmental practitioners with the investigation of PFAS at contaminated sites in BC. And this is, quite frankly, a shameless plug for that document. And that document does get into some of the specifics of contaminated sites investigations for PFAS. The Interstate Technology and Regulatory Council finalized its PFAS guidance document this month. And although it's a US focused document, it does provide good detail on considerations for undertaking PFAS site investigations. Plus, there are some really great training videos which accompany the document. Getting into the details of PFAS investigations could feed numerous webinars of material. So some very high-level considerations for sampling and lab analysis are covered on the next slides. As a site investigator, the challenges start at the project planning stage. Investigations require specialized precautions above what is considered the norm and need to be accounted for when designing and planning the investigation and establishing the project timelines. Things like thinking about pre-testing source water used for the drilling program, substituting field supplies and equipment suspected to contain PFAS, modifying sample collection methods to collect data in a way that minimizes the potential for introduction of PFAS to samples. And it also includes implementing what can be, at times, some really onerous decontamination procedures. To confirm that there hasn't been cross-contamination or unintentional introduction of PFAS to samples, it also involves the collection and analysis of numerous quality assurance and quality control samples. There are also special considerations with respect to lab analysis of the samples collected during investigations. It's important to be aware that all labs in Canada employ an in-house developed method that has been refined over time. There is no single prescriptive method that is followed by all the labs in the exact same manner. From lab to lab, there will be differences in aspects of their methods, all of which may have some impact on the final reported results and the interpretation of the data. Things like how the labs handle sediment in aqueous samples, what procedure is used for analyzing samples with different contaminant levels, and whether the lab takes a whole sample analysis approach or employs subsampling. Commercial labs in Canada are generally employing isotope dilution techniques for quantification of PFAS, but the standards that are used in the analysis may vary from lab to lab. Finally, each lab will have its own background levels of PFAS that will exist within the lab environment. In British Columbia, 2 methods for analysis of perfluoroalkyls in soil and in water were released by the Ministry of Environment and Climate Change Strategy in 2017. These methods outline performance-based requirements and are not prescriptive analytical procedures per se. Of particular note for practitioners conducting investigations in BC is that the lab manual has specific requirements that may not necessarily be met by the routine PFAS analysis offered by Canadian commercial labs. The guidance document goes into a bit more detail on this, at least the CSAP guidance document. It's critical that practitioners liaise with their project labs prior to sample collection and analysis to confirm that the method being employed will meet BC regulatory requirements. In terms of advances at commercial labs, the main progress has been with respect to the evaluation of precursors in environmental samples. In Canada, 2 options are currently being commercially offered or are expected to be offered in the near future to help with this evaluation: the total oxidizable precursor assay and total organic fluorine analysis. For those of you unfamiliar with the TOP assay, it's a lab analysis developed by Erica Houts and David Sedlak, whereby chemical oxidation is used to break down large, difficult to measure polyfluoroalkyl substances, or the precursors, into smaller, more readily identifiable perfluoroalkyl acids. The latter analysis, total organic fluorine, by either combustion ion chromatography or neutron activation analysis, is one that I won't actually discuss in detail since it's not widely available yet in Canada, but it is expected to show up soon. This analysis is intended to provide investigators with a screening tool to support the evaluation of PFAS precursor presence and absence at contaminated sites or potentially in food packaging and other materials. However, it's not expected that such a method would be suitable for demonstrating regulatory compliance. With TOP assay, samples are split and one part is analyzed using the lab's routine PFAS method, while the other split is oxidized under some very defined conditions and then analyzed subsequently using the same method as for the non-oxidized portion. The results for the 2 splits are then compared to give an indirect estimate of the amount of oxidizable precursors in the sample. One of the most common concerns with the use of TOP at contaminated sites is ensuring that precursors have been completely oxidized. This table is an excerpt from a presentation that I gave at the RPIC conference in Halifax this past June. SLR evaluated variability between different Canadian commercial labs offering the TOP assay. The results from one lab suggested that incomplete oxidation had occurred. The take-home message is that practitioners using TOP assay should liaise with their project labs to understand what metrics they are using to monitor the oxidation step, and that they also review the results to make sure the data reflects that complete oxidation has likely occurred. The second commonly voiced concern about the TOP assay surrounds the interpretation of the results. The post-oxidation concentrations of perfluoroalkyl acids are the result of a fairly aggressive chemical oxidation in the lab setting and may not be representative of processes occurring in situ. To that end, the results are not necessarily intended for direct assessment of health risks. Rather, it's thought that the value in the TOP assay is in understanding potential impacts to remediation and also to support the understanding of how PFAS concentrations in different environmental compartments may be affected over time. So once the data is collected, then what? Well, guidelines and screening values for a number of individual PFAS have been developed or are in the process of being developed by Health Canada, Environment Canada, and the Canadian Council of Ministers of the Environment. I've listed them here. Environment Canada was first to finalize guidelines for PFOS in water and biota tissues in June 2018. Health Canada has drinking water quality guidelines for 2 PFAS chemicals and has provided drinking water screening values for 9 others. They've also developed soil screening values that are protective of direct contact with soil. CCME issued their draft soil and groundwater guidelines for public comment almost 2 years ago, and they are apparently undergoing final edits and getting into the final approval process. So these are things, guidelines that we may see released in maybe about the next 6 months or so. CCME working groups are also reportedly looking at developing guidelines for PFOA. Based on the draft version of the CCME guidelines, the soil quality guidelines for human health will be limited to direct contact pathways and will not be protective of soil leaching to groundwater used as drinking water or uptake into produce consumed by humans. The draft groundwater quality guidelines for aquatic receptors has been derived to protect against direct exposure of aquatic receptors to PFOS in water, but will not necessarily be protective of food web transfers. Provincially, or at least in Western Canada, only BC has developed soil and water standards for PFAS. I will provide more detail on, I do provide more detail on the nuances of the standards in the CSAP guidance document. Alberta Environment and Parks expects to update the Alberta Tier 1 guidelines following the release of the CCME PFOS guidelines. In Saskatchewan and Manitoba, the release of the CCME PFOS guidelines will affect investigations in those provinces. Interestingly, PFOS and PFOA are also addressed in Saskatchewan's Municipal Drinking Water Quality Monitoring Guidelines. Currently, Saskatchewan's Water Security Agency is conducting a study of PFOS and PFOA concentrations in raw and finished waters. Reportedly, neither substance has been encountered in the water supplies tested to date in that study. With all the emphasis on how ubiquitous PFAS are in the environment, one may assume that it's difficult to separate out background levels of PFAS from sites where there are significant point sources. But that hasn't really been our experience, particularly in comparison to the environmental criteria that have been developed here in Canada. This slide summarizes our own general findings with respect to one of the best known PFAS, the PFOS. I've referenced a range of BC and federal environmental criteria in the far right column. Concentrations in source areas are orders of magnitude higher than background samples and are frequently higher than the environmental criteria. The message is that if you're seeing concentrations of PFAS that are above environmental criteria in a background sample, then either there's probably a problem with how the sample was collected, or the background's not in fact background and it may be affected by a fairly significant source site. From a regulatory standpoint, PFOS and PFOA receive the majority of the attention. But what about other PFAS? Should we care? In my opinion is yes, definitely. As noted on previous slides, most sources will have a variety of PFAS and short-chain chemicals, such as perfluorohexanoic acid and perfluoropentanoic acid, are frequently the predominant PFAS encountered in wastewater effluent, landfill leachate, food waste scrap, compost, as well as comprising a significant proportion of the PFAS measured at firefighting foam and electroplating sites. As manufacturers have phased out production of longer chain PFAS, short chain PFAS precursors, such as those based on C6 chemistry, have been used in replacement materials. The short chain PFAS, like perfluorohexanoic acid and pentanoic acid, tend to be more mobile than the longer chain PFAS. What we often see in groundwater systems is that these substances typically comprise the PFAS at the leading edge of plumes due to the combination of concentrations in the source zone and their mobility. Although generally expected to have lower toxicity than substances like PFOS and PFOA, these shorter chain chemicals are still expected to have adverse effects to humans and the environment at elevated levels. If contamination is identified, then what are the options? The area of PFAS remediation technologies is rapidly changing. The ITRC PFAS guidance provides a good overview of soil and water remediation technologies that have been field implemented, as well as those that have had more limited field testing and those that are being evaluated at the lab or bench scale. In terms of what is actually occurring in Western Canada, it's a short list if we are talking about what is being largely field implemented as opposed to being field trialed or pilot tested. For soil, it is largely engineered containment, whether on-site or off-site, although under the Basel Convention, there are restrictions on the disposal of waste contaminated with PFOS above 50 milligrams per kilogram. The Australian Department of Defence has undertaken a large soil washing trial, and results are expected in the near future. Even so, that trial only looked at treating 2,500 tons of contaminated soil, and at some source sites, we're looking at needing to treat up to 20 times that amount of soil. Other soil treatment methods that have been field implemented include soil sorption and stabilization. However, the long-term efficacy of this approach is uncertain. In terms of new advances in British Columbia, thermal desorption was reportedly recently used to treat PFAS in soil for one project and would have the potential to be able to treat the volume of soil encountered at PFAS sort sites. For water phase contamination, the ex situ treatment of PFAS with sorbents like granular activated carbon or anion exchange resins is fairly straightforward and has been widely field implemented, including in systems that need to accommodate some very high volumes of water. The tricky part is tailoring the sorbent based on the makeup of the different PFAS in the influent. Some PFAS sorb less strongly than others and readily break through the sorbent media. Other water phase technologies which are under investigation include things like foam fractionation. With foam fractionation, air is used to promote the migration of the PFAS to a foam phase. The foam gets extracted and further reduced. Another technology that also gets brought up frequently is injectable particulate or colloidal carbon. However, the long-term efficacy of this in situ immobilization method is still somewhat uncertain, and the effectiveness is also going to be highly dependent on subsurface geology. For those interested, the U.S. Department of Defense's Environmental Research Program is hosting a free webinar on May 7th on some recent research into innovative technologies for the treatment of PFAS in aqueous waste streams. Frequently, due to the size of the PFAS plumes and extent of impacts, we can only address the immediate source areas with our remedial technologies, which means that we need to incorporate risk assessment into our projects to evaluate human health and ecological risks from the remainder of the contamination. Because PFAS are mobile and persistent, they can migrate off-site to private drinking water supplies. Because some PFAS bioaccumulate, they can be taken up into food items like crops, livestock, or fish tissues. Conducting these kinds of sampling programs on private lands requires discussion and planning with local health authorities, as well as communication of risk with off-site property owners once you have the data. We thought it would be helpful to present the human health toxicity reference values that may be of relevance to a Western Canadian audience. Human health TRVs are available from Health Canada for PFOS and PFOA, with interim values available for 3 other PFAS. Health Canada has provided recommended TRVs for a further 6 PFAS for which toxicity literature is more limited or non-existent. For these substances, the TRVs for PFOS or PFOA has been recommended. The BC Ministry of Environment and Climate Change Strategy used the following human health TRVs to derive the BC CSR regulation soil and groundwater standards for select PFAS. Finally, because some of our Western Canadian audience members may be conducting work in Northwestern Ontario, I thought I'd present the human health TRVs for PFOS, which are reportedly preferred by the Technical Assessment and Standards Development Branch of the Ontario Ministry of Environment, Climate and Parks. Notably, these are about an order of magnitude lower than Health Canada's and BC Environment's TRVs. The Ontario Environment Ministry does not have preferred TRVs for any other PFAS at this time. For evaluation of ecological health risks, The draft CCME Soil Quality Guideline and Federal Environmental Quality Guideline derivation documents provide considerable information compiled by Environment Canada for PFOS. It's my understanding from BC Environment personnel that the ecotoxicity information provided in the draft guideline documents was also relied upon to derive the BC soil standards. The US government Strategic Environmental Research and Development Program, or SERDP, has been funding some studies which may be of interest as an ecological risk assessment resource. Guidance for assessing ecological risks of 18 individual PFAS to threatened and endangered species at firefighting foam sites was released in January of this year. Program studies currently underway include one study focused on deriving TRVs for amphibians and another on deriving TRVs for birds. Webinars related to these projects are available online at the SERDP website. And that brings us to the end of today's webinar. Sorry about the technological hiccups. Feel free to reach out to either myself or Matt if you want to discuss any information brought up during the webinar, or if you have questions that come up down the road, or we can take some questions now.
Thanks, Lindsay and Matt. That was a great presentation and lots of information there for us and a great overview. If anyone has any questions, feel free to type them and I'll relay them on. Once again, all the presentations, the PowerPoints will be posted on our webinar page at esa.org/webinars. As a PDF along with the recording of the presentation. And I think questions. Here's a question. I've heard that PFAS foams were sometimes used in landfills for odor and dust suppression. Do you know that this happened in Western Canada?
I have not heard that, no, but that's something definitely that would be interesting to follow up on.
Okay, does anybody else have any questions? Okay, looks like we don't have any other questions. So thanks, Matt and Lindsay again. Thank you, SLR Consulting, and thank you everyone for participating today. Look forward to seeing you on another presentations shortly. Thank you.